going to start recording just before I forget. Anything else before we begin? So Wednesday,
Are we,
if
sorry, Professor,
oh, go
sorry to
ahead.
cut you off. Are we still gonna get extra points for doing quiz 5?
Absolutely.
Right.
Because quiz 5 was not a quiz, I should say covered material that we did not cover. If you complete that, I will give you extra points for that. What I would probably do is drop your lowest quiz and replace that score.
All right, thank you.
Sure. That might be easier, just give everybody 10 out of 10. But no, if you take that, I'll give you extra credit on that. Okay, so let's get going. So we're on the topic of light, and we've talked about electromagnetic waves already. That was part of the essay question. And specifically, we're talking about the properties of how visible light, part of the electromagnetic spectrum, interacts with matter, how it can be absorbed, how it can be emitted, how it can create a more complex interaction we call fluorescence, how it can reflect off of things, and how it can refract through transparent media. So we're going to talk a little bit about reflection today, and refraction. And reflection, as we talked about before, is where light will come in and it will essentially scatter off of a surface. Now, when I'm looking at a sheet of paper, I'm seeing what is called diffuse reflection. And we call it diffuse reflection because the light will come in, it'll come in a nice orderly fashion, hit the surface, and as it does so, it hits all different types of topography. Light is really, really small in terms of the size of its wavelength. And usually when we have a wave coming in and it sees something that is bigger dimensionally than it is, light is about a half a micron or half a millionth of a meter. So if we have all these bumps on the surface of the paper, which are bigger than a micron or a micrometer, it's going to scatter the light in all different directions. Okay? We call this diffuse reflection. In fact, I look around the room and the walls of this room are painted with latex paint, and latex particles are small. They're microscopic, but they're not smaller than the wavelength of light. So when the light hits it, it bounces off in all directions, and I can see the walls that way. So if you paint with a flat paint, it tends to have more of a texture. I don't know if you've ever painted with a satin paint. It's a little bit flatter, and then a gloss paint would be the smoothest. But any surface that has, texture that's bigger than wavelength of light, it's going to scatter it off in all directions. And that's what, again, we call diffuse reflection. And here's a magnification of a piece of paper. You can see all the different fibers that are laced within there. And clearly, these fibers are bigger than light itself. So diffuse reflection is pretty much how we see the world around us. Most things don't give off light, okay? Most things just reflect the light, this diffuse reflection. And in this picture right here, this is actually at Yosemite Park, beautiful park if you ever get a chance to see that. But we can see the light reflecting off of the mountains. We can see, well, not really so much the trees, because the trees are really in shadow right there. It's reflecting off the clouds. It's actually even scattering off the air molecules. Okay? All the surfaces which have bumps that are bigger than the wavelength of light, we get this scattered reflection. What you see here off the lake is because it's a nice, calm day, is the lake is perfectly flat. And we get diffuse reflection in this particular case. And with diffuse reflection, the angle that the light comes in is equal to the angle that the light goes out, okay? And it gives us the illusion that these mountains right here, okay, are actually pointing downward from this reflected image. Okay, so what's going on right here? Well, I'm seeing the mountains through two different paths. I'm seeing the direct light that's coming from my eye, coming to my eye from these mountains, and then I'm seeing light that makes a bounce off the lake and then makes it to my eye. Okay, so that's specular reflection, and specular reflection we of course use to look at ourselves in the mirror, because specular reflection creates what we call an image. We are the object, okay? Light bounces off of us in different directions. And when some of the light hits the mirror, that mirror will reflect it at a very precise angle, okay? Here the light comes in. This looks like about a 45-degree angle. It will go out at a 45-degree angle. And the image gives us the illusion that there is something, beyond the surface of the mirror. Okay. So we say the angle of incidence is equal to the angle of reflection, and we can actually see this with this green laser beam. Okay, and that clearly is coming in about a 45-degree, maybe 40 degree angle, and you can see it's coming out at the exact same angle. So that is a law of reflection. The angle that the light comes in is going to be equal to the angle that the light comes out. All right, let me just see here. Hold on a second. I found the offender. Okay, I had to mute. But again, looking at most mirrors will actually use a very, very thin coating of metal. And metal reflects light just like everything else, but it's actually a very good reflector. About 85 to 90% of the light that hits a metal is going to reflect off. So the way we create these mirrors is we use glass. So we'll take a polished glass surface. And then in a vacuum chamber, they will evaporate the metal onto the glass. What they'll do is they'll heat the metal up. It'll form a vapor. The vapor will then condense on the surface. You get this little thin coating of metal, only a few atoms thick in many cases, that goes on top of the glass. The glass is transparent, so it doesn't reflect as strongly. And that's basically how we create these mirrors. So, looking at yourself in the mirror, what you're actually seeing is the rays leaving your body and then being reflected back to you. And that creates, again, what we call an image. So images are formed where if we take the light reflecting off our body, instead of thinking about them as wavefronts, we think about them as rays going off in all different directions. The images form where the rays of light will end up intersecting to form a new image that can actually be seen. So images are classified as real, okay, if we can project them onto something and actually see something reconstructed from the rays of light. We call that a real object. Or virtual, where the image appears to be at a location where it actually isn't, like inside the mirror, okay? Real images can be projected. So when you go into a movie theater, They are projecting a real image onto a screen, and you can see that. Imaginary ones are not projected, okay? So what we see in a mirror actually is called virtual or imaginary. Okay. So how do we get our image in the mirror? Well, if we think about it this way, here is our object right there, okay? We are looking at ourselves in the mirror, so we are actually the object. If we look at the light that's coming off here, we can see if we trace a ray of light to the surface of the mirror, it's going to bounce back and come in the same direction that it left. The angle of reflection is equal to the angle of incidence. It comes in at 0 degrees, it comes off at 0 degrees. This other ray right here, let me change colors, it'll be easier to see. The other ray right here comes down here and bounces off the same angle that it came in. And then I'll change colors again. We have another ray, which is coming down here. That bounces off in this direction. Another ray here that bounces off in this direction. So in many ways, this virtual image of ourselves in a mirror is actually an optical illusion, okay? It looks like we could reach into the mirror and actually touch the image of ourselves because it's the same distance that we are. But if we actually see what's going on, we're tricking our eyes into thinking that this yellow ray is coming from inside the mirror. It's not. It's bouncing off the surface of the mirror, but it has the same effect as if it came from inside the mirror itself. Same thing with the red one right here. It looks like it's coming from right here, but that reflection off the mirror gives us the illusion that it came from a place that it didn't. Same thing with the blue. Appears to have come from here, but it actually bounced off the surface of the mirror. So we use geometry. I know you all enjoyed your geometry classes. We use geometry to try to show us how those images formed from the reflection of these rays. And again, this is clearly not a real image. It's not physically there, okay? This reflected P is not inside the mirror, okay? But it appears to be there, so we say that it's an imaginary one or a virtual one. Okay. The other neat thing about a plane mirror is that, as you can see here, everything's reversed. So the P appears to be backwards when we look at our reflection. And when we look at ourselves in the mirror, what's on the right side of our face appears to be on the left side of the image. Okay, that's kind of cool. Obviously, you can take an entire course in optics, and this gets even more complicated in terms of, looking at the geometry of the whole thing. But for a flat mirror, we say a few things. The reflection is reversed left to right, okay? The image is reversed left to right. The image is right side up, and the image has the same magnification as the object, okay? So when I look at myself in the mirror, I see a person, okay? I'm looking older and older every day. I see a person who's exactly the same height as I am, okay? I'm right side up, okay? The only difference is I'm reversed left to right. So a flat mirror will do that, okay? If we curve the surface of the mirror, we can actually play some games and change the magnification of the image and also change the orientation of the image, right side up or upside down. Now, magnification, before we get into magnification, basically compares how big our image looks compared to how big our object was. Okay, so again, flat mirror, there's no magnification there, which is good. We look at ourselves in the mirror, we check our hair out, make sure that nothing, funny is on our face. Um, you know, great thing to inspect ourselves. Um, and let's skip some of this. And again, flat mirrors, there's apparent left to right reversal. And if you really want to go into the geometry, you can convince yourselves of these different things in these images. The also reversal that we get is we are reversing, when we're looking into the mirror, the image is looking out. So there's a difference in that direction too that you can convince yourself of. Did you ever notice how an ambulance will have their the front, where the right ambulance will have that reversed? That's basically because when they come up behind you, they expect you to look in your rear view mirror, your side view mirror. And when you see this, they'll reverse the letters backwards, so the mirror will reverse it again. So that's sort of an interesting aspect of these flat mirrors. Your rear view mirror actually has two different surfaces on it. Although, now they're starting to use other technology to produce these. But the old style was you could actually flip a switch and change the reflectivity of the mirror. And the way that they set these up is any smooth surface will reflect light. Okay, so your rear view mirror actually has two surfaces. It has a glass surface that's not very reflective, and a metal surface behind that glass surface that's more reflective. In the daytime setting, you will set it so the metal side is reflecting the rear image into your eyes. At nighttime, you change that so it is a glass surface which is reflecting the light. And the reason why we do this is metal reflects, again, about 85 to 90% of the light that hits it. So if somebody has their high beams on you and they're coming up from behind you, 85 to 90% of that light is going to make it to your eye. However, with glass only reflects, for straight on reflection, about 4% of the light. So that greatly reduces the glare that you see at night. So somebody with their headlights, reflecting off your mirror is going to be only 4% as bright as it would be otherwise. And again, that is the nice thing about how these mirrors work. So flat mirrors, magnification is basically 1, because our image looks as big as our object. What else? We have left to right reversal, okay? And we have forward backward reversal. But otherwise, our image appears upright and, makes it, the only thing is, if you've ever worked with a mirror, and this is something dental students actually have to learn how to do. If you ever worked with a mirror, you have to teach your body how to move, in the opposite direction. Okay. Like right now, the image that I have on my screen of myself is reversed left to right. So it always looks funny when I point in one direction, my pen's going in the other direction. When you're working with a mirror, you actually have to learn how to move your body in the opposite way that you normally would. Okay. Something really interesting happens when we used a curved surface mirror. The old fun houses at the carnivals would actually curve the mirror and would distort your image. And the reason for this is a curved surface will actually change the overall magnification of the image that you see. Now, this is what we call convex. You probably learned this at some point, that when we have a surface that bows out, it's convex. When we have a surface that bows in, the light's coming from this direction, we call that concave. I always remember this, that, a cave is a space in a rock which, goes inward. So, we can think about the surface as caving in, if you want to remember it that way. That's the way I remember it. It worked for me. But convex mirrors have a curved surface that causes light rays that are coming in all at the same direction. Okay, all in the same direction. It causes them to reflect off in what we call a divergent manner. Okay, so they're all coming in. Diverge means to spread out. So if I have all these parallel rays coming in, they're going to reflect off and basically spread off in all directions. Okay, now what does that do to the image? All right, we're not going to get the same image that we get with a plane mirror. The convex mirror will actually keep our image right side up. Okay, here's our object. Say we have a blue arrow in front of the mirror, and we look at that. We look at the mirror, and we're looking at the blue object, and we're like, wow, it's still right side up, but it's so much smaller. Now, the reason why this happens becomes apparent only if you really look at the geometry of what's happening here. This light ray comes in, bounces off in this direction, because remember, the law of reflection is such that the angle that it comes in is equal to the angle that it reflects. But if we look at this, the surface, my iPad rotates. You look at the surface, what happened here? Got rid of my pen. You look at the surface here. Okay, that didn't do so well. Let me get rid of that. Let me draw a line instead. I'm not good with drawing freestyle. Okay, there we go. That represents the direction perpendicular to the surface. So clearly we can see the angle that the light came in is equal to the angle that the light is reflected. All right, so what does that do? Well, again, here's the ray coming in, but it appears, as it reflects off in this direction, it appears to be coming from this way. This ray bounces right back at us and appears to be coming from this direction. All right, so both of these rays, I know this is a little complicated and I apologize, but both of these rays are coming from the top of the arrow. In fact, I can come up with more rays that come from the top of the arrow. Like if I do one right here, this will appear, this will reflect off at the same angle, and thus will appear to have come from the top right there. So all the rays that are reflecting from the top of that arrow are coming from that point right there. And we can convince ourselves by playing a little bit of geometry that that's where that image actually originated from. Okay, it's smaller, all right, but that gives us an advantage in some cases. The fact that it makes all the images smaller than the objects, it allows us to see more than we would actually be able to see otherwise. Now, in a flat mirror, you can only see what is in your field of vision, how big the mirror is. But with a convex mirror, we compress all the images, making them smaller, so we can fit more on this, and we can see much more. Now, here's a convex mirror showing the image of a candle, but do you notice we can actually see the reflection of the entire room? Okay, whoever took this, there's the camera right there. Hey, there's a camera right there. We can see blackboards, okay? We can see other things. We can see the entire room, even with a very small convex mirror. So it gives us a big field of view, even though the images look smaller, okay? Where would this be an advantage? Well, in a convenience store, okay? These security mirrors are really inexpensive, much cheaper than putting up cameras, although cameras are getting cheaper and cheaper. You'll see these in stores to prevent shoplifting because it allows the viewer, who's ever working the register, who's ever at the store, to see a much larger part of the store than they'd otherwise be able to see. In driving, we use them on the side view mirrors because it reduces our blind spots. If we just used a flat mirror there, it'd really be hard to see on the right side view mirror everything that was coming up on the side of our car. But again, by making the images smaller, by compressing those images, we're able to see much more than we could. So convex mirrors, everything stays upright, okay? So it doesn't invert the image. Still has a left to right, reversal, okay? And its magnification is always negative. Now, concave mirrors, these are these are sort of multiple personality mirrors. You think, well, convex makes things smaller, concave makes things bigger. No, not always. Concave mirrors have two different types of images. They have a virtual image, like the flat mirror, like the convex mirror, but they also can produce a real image too. Now, here we see that same setup we saw before, but this time we're using a concave mirror. If we place the object close to the mirror, okay? By the way, you can look into this in more detail. These mirrors have a focus, they have a center of curvature. We're not going to talk about this in too much detail because that's really the subject for a geometric optics course. But when we place the candle close to the mirror, what do we see? We see the candle is upside down, and in some cases, we can actually magnify the candle. We'll see that in a second. So if we place the candle in front of the focus, we can inverted image, and normally the image is upside down. Okay. If we place it in front of the focus, what do we see? Well, the image is distorted, okay, but it's larger and right side up. So here's that multiple personality thing. Things that are much closer are magnified and right side up. Things that are much further are inverted and the magnification is lower, okay? Now, Sir Isaac Newton was the first to realize that these concave mirrors could be used to magnify images. Before Newton, Galileo had used lenses to magnify images to create his telescope. So Sir Isaac Newton used concave mirrors to create the first reflecting telescope. And this is known as the Newtonian reflector. It was really quite ingenious. He would grind a piece of glass, smooth, concave, just like you would for any telescope. But instead of using the glass as a lens, he coated the glass, I believe he coated the glass with mercury, which is a reflective metal. And this created a reflective surface that he could then send the light to a secondary mirror. This would take the light rays and move them out of the focal plane. And then he would mount an eyepiece off to the side and form an image from this. This was a tremendous improvement over Galileo's telescope for a number of reasons. First, I'm only grinding one surface. I'm only doing one surface of this mirror, okay? If I were to make this into a lens, I'd have to polish both sides, so I'd have twice as much work. Also, unlike Galileo's telescope, which had a tremendous problem with chromatic aberration, we'll talk about that later, it spreads out the colors. This didn't suffer from chromatic aberration. In fact, Newton's invention was such an improvement, we still use it today. Here's the Hubble Space Telescope. It uses a concave mirror, a little bit more complicated than what Newton had used. This is actually a hyperbolic mirror rather than a parabolic mirror or a spherical mirror like Newton used. But we use the same exact invention to create these research telescopes. Here's the Keck Observatory. It was at one time the largest. It's barely under the largest. And what's kind of cool here is because it's hard to make one big mirror. Can't see it so well here, but they've actually created many reflective surfaces, many different mirrors as these hexagonal tiles, and they put them together as one big telescope. This is on Mauna Kea in Hawaii, and there are three really excellent places to look at the nighttime sky. One is Hawaii. It's a big shield volcano, so the air that blows, atmospheric wind that blows above it, stays relatively stable. The other place is the Atacama Desert in Chile. That's a very high altitude. It's very dry up there, so it's a great place for telescopes. I think that's where they have the largest telescope in the world. And the Canary Islands are another volcanic island off of Europe and Africa, which have excellent viewing too. So those are the three best places to actually build telescopes. Okay, this is the Gran Telescopio Canarias, which I butchered its name, but this is in the Canary Islands, and it is the world's largest telescope at the time at 10.4 meters. I think they're building a 30-meter telescope in Hawaii, and they're also building another big telescope in Chile. And obviously, as the technology improves, the big problem is we can't build a mirror that's too large because as we move the mirror sags. So they actually have computer-controlled actuators that maintain the shape of the telescope. And as the telescope gets bigger, the actuators have to be more and more sophisticated. Okay, so that's reflection. Okay, and again, we probably come across reflection every day. Before I come to class, I do look in the mirror to make sure that nothing crazy is going on with my face. Try to comb my hair and look somewhat professional. But obviously mirrors are a important invention that we have, not only to look at ourselves, but also for driving a car. Having those extra mirrors really helps us see what the traffic's doing around us. In convenience stores, they're used for security. In astronomy, they're used for telescopes. So light reflecting off surfaces can be thought of light as bouncing off surfaces. Refraction's a little bit of a more subtle effect. Refraction, the simplest way we can think about it is light comes in and then it suddenly changes its direction as we go from one medium to another medium. Now, why this happens, why does it come in one way and then suddenly decide to change its direction? Well, it has to do with speeding up and slowing down the light. anytime we speed up or slow down light, we can refract it or change its trajectory. Now, light travels at 3 times 10 to the 8 meters per second, okay? Incredibly fast. However, when light enters some other medium, such as water, as we can see up here, light's going through water, it actually slows down to 2.5 times 10 to the 8 meters per second. In fact, in glass, it slows down even more, down to about 2 times 10 to the 8 meters per second. So refraction takes place as the atoms, they don't absorb or reflect or transmit light, but they use their own electric fields to interfere with the light and slow it down a little bit. Now, there's something called the index of refraction. This little letter N represents how much we're really slowing down the light. The index of refraction is the speed of light divided by the speed at which it's going through some medium. Okay, now, what does that mean? Think about glass. In glass, the speed drops basically to about 2 times 10 to the 8. So if I take 3, oops, I don't know why my pen didn't come up. Okay, if I take 3 times 10 to the 8, which is the speed of light in a vacuum, that's always the speed of light in a vacuum, and I divide that by 2 times 10 to the 8, 10 to the 8 divided by 10 to the 8 cancels out. I got 3 over 2. 3 halves is 1.5. So roughly in glass, the index of refraction for some glass is 1.5. Okay? Now, if I were to slow down light even more, let's say I slowed it down to half of its speed, okay? Which I think is pretty close to what we do in diamond. Okay, oops. So again, on top, I always have 3 times 10 to the 8. That's always the speed of light in a vacuum. I divide it by 1.5 times 10 to the 8. 10 to the 8 cancels out with 10 to the 8. 3 divided by 1.5 is 2. That would be an index of 2. So index of refraction kind of works backwards. The index of refraction is really the inverse of how much we're slowing, how quickly the light's going through the medium. The higher the index of refraction, the slower the light travels through there. Sorry about that. Okay, so let's look at a few different materials and see how the index of refraction changes. All right, here is the index of refraction for air. Makes sense. There aren't many molecules in air. Air is mostly empty space, so it's not going to really change the speed of light very much. Okay. Water slows down light a little bit, so its index of refraction is 1.33. In ice is a little less dense, so it's 1.31. Okay, so it slows down, about a third. Now, glass is a generic term for any amorphous transparent material normally. Okay, actually, if you're, in some fields of science, glass doesn't even have to be transparent, but we'll consider glass to be optical glass. Okay, all right, so some glass made of fluorite is fluorine and carbonate, will have a very, very low index of refraction. Quartz has a slightly higher index of refraction. Quartz is pure silicon dioxide, okay? But we can put things in the glass to replace the silicon, such as crown glass has a little bit of sodium in it, okay? Flint glass, we used to put lead in it, but lead's toxic, so I think they've replaced that with titanium. Extra dense flint glass, so you can see even what we call glass itself can have a wide range of indices of refraction depending on what we put in the glass itself. Okay, so again, if it's just pure silicon dioxide quartz, that index of refraction will be almost about 1.5. As we add more and more other materials, and again, it used to be lead. We don't really like to use lead anymore. Now we use titanium, becomes titanium dioxide. As we add more and more titanium dioxide, the index becomes greater and greater because titanium slows down the light more than the silicon dioxide does. Zircon is not cubic zirconium, okay? But zircon is another transparent material. And here you can see diamond is almost an index of 2.5. So the speed of light in diamond is like traveling at 1.3 times 10 to the 8 meters per second. And that's very important. The reason why diamonds are so prized is because they have a very high index of refraction. And this can lead to special effects that we call total internal reflection. A diamond looks very different than glass because it can bend the light in ways that glass cannot. All right. So again, glass is a term we use to talk about materials without any definite structure. In optics, it usually means, silicon dioxide mixed with something else. And again, crown glass. Oh, I said sodium. Crown glass has been traditionally made of silica and alkali oxides such as potassium oxide. So, not just sodium, sometimes they'll use potassium in there too. Here's flint glass, traditionally anywhere from 4 to 60% lead oxide. However, now we're using more titanium dioxide and zirconium dioxide and even lanthanum dioxide to get that higher index of refraction. Flint glass is used in stemware quite a bit because not only does it refract the light quite a bit, you can etch into it. Why isn't my test? Okay, well, I'm lost my ability to draw on this. Don't know why it's having that problem.
Probably froze.
Yeah, I guess my iPad froze. Stupid iPad. All right, I'm gonna put that down. At least you guys are still here, so we can go on. Diamond has the highest index of refraction of any really transparent material, and again, yeah, my iPad's decided to go to sleep. I don't know what it's doing. But at 2.42, high index of refraction, but it also has a large, what we call total internal reflection. Now, total internal reflection, I'm going to skip this Snell's law. If you want to go into more geometric optics, Snell's law is such an important law. It basically relates the index of refraction to the angle that the light comes in. So the index of refraction times sine theta, where theta is the angle, means that as we go into a slower material, the angle has to become less because the index of refraction is becoming greater. Now, believe it or not, the sun sets before the sun sets. Our atmosphere refracts the light from the sun, so the sun is still seen above the horizon even after it's gone below the horizon. If there were no atmosphere, the sun would appear slightly lower in the sky than it actually is. but we get a few minutes extra, and that's really important during this time of the year. We get a few more minutes of sunlight because of this refraction effect. And here we can actually see that happening to the moon. The moon sort of has a squashed image when we view it from orbit due to this refractive effect. So when the sun is actually set, we can still see it slightly above the horizon. We get that sort of squashed look because of the different refraction going on here. Lenses, of course, are important for focusing images. And instead of using a curved surface to reflect the light, here we use a curved surface to bend the light. And the way it works is, with convex lenses, they can focus rays to a point just like the concave mirror was. For concave lenses, they diverge the light, okay? So a convex lens acts like our concave mirror. A concave lens acts more like our our convex mirror. Okay, here we can see with the magnifying glass, we can magnify the image when we hold it very close up. So concave lenses are used for that. When an object is more distant, it inverts the image. When it's close up, it magnifies the image. For a diverging lens, it makes everything look smaller. Okay, and refracting telescopes and microscopes can use both types of lenses, but usually uses mostly convex lenses to produce an image. Now, the reason why we use more than one lens is with just a simple magnifier, we can only magnify to about 10 times, okay? We try to magnify more than that, the image becomes very distorted and it's really not of much use. Microscopes and telescopes allow us to form an image which we can then magnify using an eyepiece, and this allows us to magnify as much as the light will allow us to magnify. For a telescope, the size of the objective determines how much we can magnify the image. For a microscope, we can't magnify anything more than the wavelength of light. And again, here's a very complicated image showing us how we form the first image, and then we use the eyepiece to magnify the second image. Okay. Again, we would spend an entire day on discussing microscopes and telescopes to understand the geometry here. But refraction can also be used to create optical illusions. This is called a mirage. Now, mirage, some people think from cartoons, mirages are actually hallucinations. Hallucinations are not mirages. Mirages are created when the light bends in such a way that it looks like it's reflecting off of a liquid surface. Mirages in the desert were caused by the sand getting very, very hot and bending the light as the air becomes less dense, and it refracts the light less. So the light off the hot sand would look like it's reflecting off of a liquid surface, and you'd have the illusion that, oh, there's a lake up there, where if you're in the desert and you're out of water, would be a really cruel trick. But again, what happens here is the cooler, denser air above the ground, okay, slows down the air more than the hot air, which is closer to the surface. So what happens is that light always bends toward the higher index of refraction. So when we look at an image, we are getting a direct image from the object, but we're also getting a refracted image that makes it look like the object is reflecting off of a shiny surface. It's not, okay? There's no water there to reflect the surface. Okay, we're almost out of time. Total internal reflection. happens when refraction bends the light so much that it can't escape inside a particular surface. Now, when light comes directly toward a reflecting surface, it'll bounce right back. The angle of incidence is equal to the angle of reflection. Some of the light, if it's transparent, will go through, as we can see right here. Light comes in, or going from here. Light goes in, some of it reflects, some of it goes out. As we make the angle steeper and steeper, what happens is we reach a point at which we can't refract the light out of there anymore. So basically, total internal reflection means all the light that's inside there is going to stay inside there and simply reflect. This is important for things such as fiber optics. The beam of light, we would think some of it could escape, but if it did, it would refract at a 90-degree angle. So total internal reflection has 100% of the light reflecting backward. In a fiber optic, if we use a high index refraction core and a lower index cladding, the light can't escape. We'll keep bouncing back and forth. And this is really, really important for sending data, because if we use mirrors, at best, mirrors can reflect 85 to 90% of the light. Okay? That means that every reflection, we lose 10% of the energy. If we had simply a reflective hollow cable to bounce the light back and forth, after a very short distance, we wouldn't have very much light there. In total internal reflection, 100% of the light reflects. So fiber optics can send the light for kilometers. And that is done, at a very steep angle. Okay. Now, again, going back to the diamond having a high index of refraction, if you cut glass in the shape of a brilliant diamond, you can tell it's fake because the light will pass right through the glass. With a diamond with a really high index of refraction, the light will hit the back surface, bounce off, then come back to your eye and look much brighter. That's why we call it a brilliant cut, because if it's done for a diamond, all the light that goes in will be reflected back to your eye. It really makes the diamond look, spectacular. Quickly, our eye is an incredible optical device. Our eye is basically a system with two lenses up front that focuses the light on a nerve sensitive area we call the retina. So when we look, it's actually the cornea, the outer clear part of the eye, that refracts most of the light. And then this little lens inside here does some of the adjustment. Okay. As you look further, the lens will flatten out so it doesn't focus the light as strongly. As you look closer, the ciliary muscles relax and allow the lens to get fatter to more strongly focus the light on the back. So the cornea bends most of the light. You can see it even looks like a lens. Okay, it even has that curvature. So it's a convex lens. Then goes through the lens, which will focus the light even more, and then project an image onto the back of our retina. What's interesting is when we look at an image, okay, the image is actually inverted. It's actually upside down on our retina, and our brain turns it right side up. Now, if you're nearsighted like me, I can't see off into the distance very well. Things are blurry. That's because the light that comes from distant objects, okay, focuses in front of my retina. To correct for that, I wear glasses. And these are concave lenses. They diverge the light a little bit so that the light can then be focused on my retina. If you're farsighted, that means that close-up images can't be focused. To correct for that, we use a convex lens. Now I'm getting up in years, so I went to the eye doctor. They told me I don't need bifocals yet, but there's a condition called presbyopia, after a certain age where you can't focus far and you can't focus near. So what they do is they give you multiple vision glasses, essentially bifocals. Benjamin Franklin invented bifocals. Part of the lens is a concave lens, so you can see far. Part of the lens is a concave lens, so you can, convex lens, so you can see near, and they blend the two together to basically allow you to have both those visions. Okay, what happens is that ciliary muscle that makes your lens get fat and thin, as your lens grows, it has no way of shedding new old cells, so it just gets thicker and thicker and thicker, and eventually that creates a slackening in the tension of the ciliary muscles. You can't focus anymore. If you get laser surgery, what they actually do is change the shape of your lens. Now, most laser surgery doesn't use razors anymore to cut into your cornea. Most laser surgeries can be done all with lasers, with excimer lasers. Not excimer. I'm trying to think what type of laser they use. But in any case, an ultraviolet laser will change the shape of your lens. My lens is too curved. Okay, so if I were to get LASIK surgery, I would they would take material from the center to reduce the curvature. If I were farsighted, they would take material from the outside to reduce the curvature. What else? Oh, we're out of time. The iris regulates how much light comes in. The lens, as I said, accommodates our vision. And the retina are nerve cells that are light sensitive that turn the image into something our brain can process. All right, folks, I'm out of time. Once again, we will not meet this Wednesday. So if you did not take test 2 yet, show up on Wednesday. You are taking test 2, the makeup. I'm making a makeup version for that. And otherwise, have a great Thanksgiving, everybody.
You too,
Okay.
Professor. Thank you.
Thank you, Professor.
Thank you, you too,
Bye.
Professor.
Dr. Hibbert.
Take care.
Bye-bye.